Let's start with several introductory words. Word problems are the bread and butter of mathematics, one of its most important parts. Usually at this entry level, word problems are solved using equations and word systems. After writing an equation or system, we can solve it, and here it is, the solution. This is a direct and effective method of solving problems. But what we gain in simplicity, we lose in the depth of the understanding of the intricate connection among the elements of our problem. By contrast, arithmetical methods are more difficult methods of solving word problems, often characteristic to a particular kind of problem, which require a mental gymnastics, but revealing simultaneously surprising internal links. Arithmetical methods teach us not only to think out of the standard way, but also to write and display ideas in different non-conformist ways. I'm presenting, along with specific arithmetical techniques, some of the most important methods known to me, of course, as, for example, method of reduction to unit, method of comparison, the method of additional assumption, and so forth. Now let's start by speaking about technical notes. What do I mean by technical notes? I mean how to avoid writing an equation from a given data. So we have data. Usually we write equation from those data. How to avoid that? Yes? And I'm starting with specific situations. Let us suppose that 48-foot rope is cut into two pieces, A and B. Could we find the length of each piece? Of course not. Why not? Because we don't have enough information. The only information which we have is the sum is 48. In order to find the length of the two pieces, we have to have additional information. And let's start with some situations. Let us say that the two pieces have equal length. Then if the two pieces have equal length, then the length of each piece is very easy to find. 48 divided by 2. So 24. So the length of each piece is 24 feet. Was not very difficult. Now, a new situation. Let us say that the piece A is 2 times longer than the piece B. Then how do we find the length of each one? Well, if the piece A is twice as long as B, if B has 1 part, then A has 2 parts. So in total, 3 equal parts. So if we divide 48 by 3, 16, here is the length of the piece B. Why B? Because B is 1 part. And the length of the piece A is, of course, 16 times 2 is 32. Now, let us see another situation, new situation. Let us say that the ratio of the length of the piece A to piece B is like 3 to 5. How to find the length of each one? So this means that if the piece A has 3 parts, the piece B has 5 parts, for a total of 8 parts. So 48 divided by 8 is 6. So therefore, the piece B, the piece A is 3 times 6, 18 feet, and the piece A is 5 times 6 is 30 feet long. In this, now another new situation. Let us say that the piece A is 6 feet longer than the piece B. The piece A is 6 feet longer than the piece B. How do we find the length of A and B? Well, let's think that we make shorter the piece A by 6. What impact will this action have on my data? If we make the piece A shorter by 6, then the piece A and B will have the same length. But not only that, but also the sum of the piece A and B will be 6 feet shorter. So instead of 48, will be only 42. So if therefore if we consider then that the sum of the 2 lengths is 42, then the 2 lengths are equals, so each one is 21. So the piece B is 21. Why the piece B? Because the piece B was not changed. The piece A was changed. And therefore, the piece A is 21 plus 6 is 27. Yes? Now, somebody would say why would I make the piece A shorter with 6 feet and not making the piece B longer by 6 feet? So here is an alternate method. Yes, let's make the piece B longer by 6 feet. Yes? What will this have, what will this do to our data? Once more, the two pieces will have the same length. But the sum of two pieces, instead of being 48, will be now 6 feet more, so therefore 54. So therefore, in this situation, 54 divided by 2, because the two pieces have equal length, is 27. And the other one is 6 feet shorter, 21. Here is an alternate method to find this. Now, here, in this situation, what I have done, I have solved a system, a very easy system. To say that the piece A is 6 feet longer than the piece B means that A minus B is 6, yes? And to say that their sum is 48 means A plus B is 48. So here we have the system A plus B is S from the sum, A minus B is D from the difference. And here we solved this system and got A S plus D over 2 because we increased, and B is S minus D over 2 because we decreased the S. So these are results which are very common, and we use them often in our problem exercises. Now, because let's go and do some other important observation before we start solving problems effectively. I'd like to speak very fast and say few words about directly proportional, inversely proportional quantities, and the unit rates. Directly proportional quantities. Let's say Mark is mowing lawns, and we suppose that he mows always at the same speed. For example, let's say that he mows 2,000 square feet in 30 minutes. From here, 2,000 in 30 minutes. From here, we infer that he mows 4,000 in 60 minutes, 6,000 in 90 minutes, 1,000 in 15 minutes, and so forth. What do you see here? You see here that if I multiply this by 2, this number multiplies by 2 as well. If I multiply by 3, this number multiplies by 3 as well. If I'm dividing by 2, this number divides by 2. This kind of quantities related to each other are called directly proportional quantities. So the quantities, when one gets double, the other one gets also double. When one is triple, the other one multiplies by 3, and so forth. Do we know directly proportional quantities? Yes. Assuming a constant speed, no interruption, and so forth, the amount of work done by someone or by a machine and the time are proportional quantities. Assuming a constant speed, the distance traveled and the time are proportional quantities. Assuming a constant debit through a pipe, the volume or the quantity of liquid flowing through that pipe and the time necessary to flow are proportional quantities. Are there quantities which are not proportional? Plenty. For example, the area of a square and its side. If the square had the side, let's say 5, then the area is 25. If we double the side, 10, the area becomes 100. So the area is multiplied by 4, not by 2, as to proportional quantities. Another example, the volume of a sphere and its radius. If we have a balloon with a radius 2 feet, then you know very well the volume, its volume is 4 times 8 is 32 over 3, yes? If we double the radius is 64 times 4 is 256 over 3. Multiplies 3, is increasing 3 times. Now, other quantities, inversely proportional quantities. Let us suppose that a team of 4 workers perform a task in 12 hours. 4 workers in 12 hours do a task. If we double the number of workers, the task will be performed in half of the time. So if one multiplies by 2, the other one is divided by 2. If we triple the number of workers, the time divides by 3, and so forth. These are inversely proportional quantities, which are quantities related to each other, in which by increasing one twice, the other one decreases twice. By increasing the one 3 times, the other one decreases 3 times, and so forth. And finally, about examples of inverse proportional quantities. the speed and the time to cover a given distance. If we go from Kalamazoo to Grand Rapids, if we have a 40 miles per hour speed, we cover this distance in, let's say, an hour. If we have 80 miles per hour speed, then the time will be cut in half, and so forth. Another situation is from geometry, for example, when the area, the length and the width of a square or of a rectangle of given area. The area is fixed. If the length is cut in half, in order the area to be the same, the width have to be increased twice, and so forth. Here, I'd like to make a last observation about unit rates. And let us assume that a gallon of water flows through a pipe in 3 minutes. The quantity of the water, the volume, and the time are directly proportional quantities. Now, generally, what we want, do you see, one of these two numbers, 15 and 3, to change in 1, to have a unit rate. For example, if I want to find a time necessary for 1 gallon of water to flow through that pipe, how long will it take? Then I will divide both sides by 15, because 15 over 15 is 1. So 3 over 15 is 1/5. So we'll take 1/5 of a minute, so which is 12 seconds to flow through that pipe 1 gallon. To the contrary, if I want the time, what is the quantity which flows through the pipe in 1 minute, then I will divide everything by 3. So 5 gallons of water flow in 1 minute. And not only this, but in some other situation, we might be asking to be here one of these two numbers to be another given number. And we perform the given multiplication or division. And now, let's start our stuff. The first method of solving word problems is the method of reduction to unit. What is this method? This method is the most common and consists in finding a unit rate, usually. Finding a unit rate and using that unit rate to solve that problem. The first example is the example with the percentages. You may remember that I spoke some times ago about percentages, and I was not exactly in the same range as the people. I said that when you say that 7% is the interest given by this bank, I said 7 is the percent, not 0.07. How is the situation here? And 7, if you attach the sign percent, then you say, here I'm speaking about percentages. And 0.07, which here is named the percentage, I said this is the decimal number which expresses the percent. And why did I do this? Because I wanted to be consistent with myself. What do I mean by that? By that, I mean when we speak about percentage, I mean per 100. $7 for $100 the banks gives me. When I'm dividing 7 by 100, what I'm doing, I'm finding how much it gives me the bank for $1, not for 100. So the bank is giving me 0.07 dollars per dollar. So is not per 100, is per 1. Okay, now how much interest make 8,500 deposited for 1 year in an account that pays 6.5 interest? 6.5 interest, like I said, means that $100 make in 1 year $6.50 in interest. So therefore, $1 will make 6.50 divided by 100, which is 0.065. So therefore, from here, very straightforward, 8,500 bucks will make 8,500 times more. Yes? So 8,500 times 0.0065 is 552. And this is it. This is the first example. The second example. The second example is the following. Do you see? If 2.35 pounds of coffee sell for $20.68, how much will it cost 3.5 pounds of coffee of the same quality? Now, a good five grade student will do, here it is, 2.35 da 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 pound, da 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 da, what? 20.68 dollars. So therefore 3.5 pounds, da da da, X. Yes, this is what a 5th grade student will do. So 2.35 over 3.5 equals 20.68 over X. So X is from here 3.5 times 20.68 over 2.35. And here, of course, bucks, dollars. Yes, this is one way to do this problem. But there is another way which reveals a little bit more. So if 2.35 pounds is selling for 20 bucks, 2068 divided by 2.35, which is 880, $880 per pound. This coffee is sold with $880 per pound. So therefore, 3.5 pounds will sell 3.5 times more than 880. And here you multiply 880 with 3.5 and get the number. Do you see here? Do you see here? This is the number which the 5th grader used. But he, the interpretation that this number from here represent how much is sold in one, for how much cost 1 pound is lost. This interpretation is lost. We no longer have this. Okay. Now, a little bit more. Now, problems involving work. And these, I used to call them work problems. And finding the unit rate, the reduction to unit, is a very important step in solving this kind of problems. What is the kind of problems I'm speaking of? Jane and Tim work at a project. They estimated that Jane working alone complete the project in 3 days, Tim in 5 days. How fast can they complete the work together? Yes? Jane does the work in 3 days. Then in 1 day, she does 1/3 of the project. Tim does the work in 5 days. In 1 day, he does 1/5 of the project. supposing that they don't fight together, in one day, they do together 1/3 plus 1/5. Which is what? 8/15. So in one day, they do 8/15 of the project. And here is the situation when I said previously, we want one of these numbers to be 1. Here in particular, I want to be 1 because I want the whole project. So I will multiply both sides by 15/8. And I have the whole project in 15/8 days. So they together do the project in 15/8 days, which is 1 day and 7/8. Yes? A little bit more sophisticated, more complicated problem is the following. It takes 5 hours to an inlet valve to fill an empty pool. And it takes only 3 hours to an outlet valve to empty half of the pool. Now, if the pool is half full and both valves are on, how much water is in the pool after 3 hours? Yes? This is a little bit more complicated. It takes 5 hours to fill the pool. So, in 1 hour, the inlet valve fills 1/5 of the pool. It takes 3 hours to empty half of the pool. So, in 1 hour, it empties 1/2 times 1/3, which is 1/6 of the pool. Now, in 1 hour, fills 1/5 of the pool. In 1 hour, empties 1/6 of the pool. Of course, 1/5 is larger than 1/6. Yes? Because the denominator is smaller. And when the denominator is smaller, the fraction is for the same numerator. When the denominator is smaller, the fraction is larger. So therefore, when both of them are on, the level of water is rising, because goes in more water than comes out. So in 1 hour together goes 1/5 minus 1/6, which is 6 minus 5, 1/30. Of the pool. So therefore, in 1 hour, the pool is raised, the water of the pool is raised by 1/30 of it. Now, in 3 hours, what will it be? In 3 hours, because if the pool is half full, do you see? Because we start with 1/2 plus 3/30 is 1/2 plus 1/10 is 6/10 is 3/5. So 3/5 of the pool is filled. So from 1/2 to 3/5, a little bit more, 3 hours. Okay. The last problem of this type is the following. I imagined this problem, so I didn't find in any book, but I try to. There are 3 people. There are 3 people, Jim, Matt, and Don, to do a job. Jim does the job in 8 hours. Dan does the job in 10 hours. And Matt in 12 hours. Now, they start the job and work together for an hour. And after an hour, Matt is leaving and remain only Jim and Dan. And they work more, 3 hours more. And after that, Jim is leaving and remains only Dan. How long will Dan work to complete the job? Do you understand? Huh? Once more, they work together for 1 hour, all 3 of them. The 2 of them work together for 3 more hours. How long will it take? And after that, works only Dan. How long will it take Dan to complete the job? It's not difficult. It's only So when they work for first, all 3 of them, in 1 hour, they work 1/8 plus 1/10 plus 1/12. You understand that? Yes, I'm trying to get a little bit faster. After that, work only these 2 guys. So, but they work for 3 hours. So, plus 3/8 plus 3/10. And here it is. What is this is the work done after working 1 hour and 3 hours. And now, what is this? I did 3/8 plus 1/8 is 4/8, so 1/2, plus 1/10 plus 3/10 is 4/10, so 2/5, plus 1/12. The common denominator is 60. 60. Here 30. Here 24. Here 1. No, here 5. Is 30 plus 24 is 54, 59 over 60. So after Jim left, 59 over 60 of job was done, so remained to be done over 1 over 60. 1 over 60, and then 1 over 60 of the job is done in 1 over 10 hours. No, 1 over 10 hour is done in 1 job, 1 hour. And now I want here to be 1 over 60. So no, what is here? Let me go again. Dan does 1 over 10 of the job in 1 hour. Yes. How about 1 over 60 of the job, which remained after this? How much? So I will divide by 6. Do you see? Because this is this one divided by 6. 1 over 6 hours. 1 over 6 hours is 10 minutes. So Dan has to work only 10 minutes to do alone, to complete alone the job. And this is it. Yes, this is this is the reduction to unit method. Some examples of reduction to unit method. Now, the method of additional assumption. Now, I'd like to tell you something. In Romanian books, this method is called the method of false hypothesis. False hypothesis. I didn't want to translate false hypothesis ad literam, because the word false may introduce something which students might say, if it is false, then it is not true. So therefore, is not true. No, is not that. We make an additional assumption. And here are 3 examples of this method. The first example is the following. Let us start with this second example. This second example, this is a problem which I worked with my granddaughter several weeks ago. She had this problem, and she did solve it. She did solve it. Not exactly the same numbers, but the type, the structure is the same. In an expo of bicycle and tricycle, there are 65 items. Together, bicycle and tricycle. We understand bicycle has 2 wheels, tricycle has 3 wheels, yes? And those items together have 149, so 65 items and 149 wheels. How many bicycles and how many tricycles are there? And the idea is to think, oh, if you want, let x and number of bicycle, y number of tricycle, then x plus y equals 65, and 2x plus 3y equals 149. Here is the system. Solve it and you are done. Not this. Not so. Yes? Number of bicycle plus tricycle together 65. Bicycle have 2 wheels, so 2x. Tricycle have 3 wheels, so 3y equals the number of wheels. Not difficult. Not so. Let's do a little bit. I would not say better, different. I want from the beginning, I didn't say that at the beginning, but I want you to know that I'm not advocating for throwing to the trash systems and all that. No. These arithmetical methods give you some more flavor to the problem, gives you more information. Now, how to do this? Let us assume that all of them were bicycles. Bicycle. All 65 items are bicycles. How many wheels will they have? They will have 130 wheels. 65 times 2, 130. Yes? This is the additional assumption. But they were not only bicycle. They were also tricycle. So here we have 149 minus 130, 19 more wheels. Why do we have 19 more wheels? Because there were also tricycle there. Now let's imagine that we take a bicycle from those 65 and put it instead a tricycle. The number of items will remain the same, 65. But the number of wheels will increase by 1. If we replace 2 tricycles, the number of wheels will increase by 2. So, why there are 19 more wheels? Because we replace 19 times a bicycle by a tricycle. So there are 19 tricycles, and what? How many? 19 minus 65, 35, 36 bicycles. Yes? 46 bicycles, sorry. Yes? This is the method of additional assumption. The second problem, the parents and the children of a school in Grand Rapids decided to make a trip to Chicago. And they found a company that charged $54 per adult and $31 per child. And they were, so $54 per adult and $31 per child. They were 43 peoples who made the trip. And from them, they paid a total of $1,747. How many children and how many adults made the trip? Yes? The same. Let's suppose that the trip was made only by children, that all 43 peoples were children. Then how much did they pay? They pay 43 times 31. And 43 times 31, sir, can you give me 43 times 31 is how much? 1333. This much? Okay. Okay. But, so therefore, they paid 1747 minus 1333, 414. 414 more dollars than the sum initially paid. Yes? Where does this 414 come from? It comes from the fact that in the bus were not only children, were also adults. Yes? If I'm changing a child with an adult in the bus, the number of persons remains the same, but the number of the pay will increase by from 31 to 54. What is from 30? $24. $23. Yes? So, how many times goes 23 in 414? 18. So, there were 18 times we replaced child with adult. So, there were 18 adults and 25 children. And here is. Now, the last example of this wonderful method is something which almost all of you, I'm sure about that, almost all of you solved. I don't see where is. Oh, would you please give me that brush? Thank you. Almost all of you taught this kind of problems. They are universal. Well, I used to call them two accounts problem when I was directing students at Western. And this is the problem. Maria has $4,400 in 2 accounts. And I'm showing you this problem to see how far the reach of this method is. 4,400 in 2 accounts. And one account gives 3.5% interest, and the other account gives 4.9% interest. The total interest for the 2 accounts was $190 and 40. Do you remember how did you solve this problem? You solve this problem this way. The table. Here is what is here? Here is the sum. Here is the percentage. Here is the interest. 3%, 3.5%, 4.9%, and total. Yes? Do we know how much is the sum at 3%? No, we don't. X. Do we know what is at 49? No, we don't, but because the total is 4,400 is 4,400 minus X, and the total is 4,400. Here the percent is 0.035. Here the percent is 0.049. The interest is 0.035 times X. The interest is 0.049 times 4,400 minus X. And here the total interest is 190.4. And now the equation, the interest from this account plus the interest from this account equals the total interest. 0.035 plus 0 times X, 0.049 times 440 minus X equals, this is the equation. Solve this equation and find X. Now, let's do better. Not better. No, not better. Let's do different. Let us assume that the entire sum was at this rate. So what will the interest be? The interest will be 4,400 times 0.035, which is what? 154. So Maria didn't have 154 bucks in her account as her interest. She had 190 minus 154, which is 3640. 3640. Thank you. So here are this money. She made more money. Why? She made this money because she didn't have money only in this account. She had money in this account too. In this account, for $1, do you remember? For $1, she made 0.035. In this account, for $1, she made 0.049. So the difference for $1 is 0.014. So for having money in this account, she made for each dollar 1 cent plus 1.4 cents more. So how many times goes 0.014 in 36.4? 2,600. So she made 2,600. She had $2,600 in the 4.9 account, and for this account it remained whatever, 1,800. Yes. Here it is. Stop here.
No count. Well, no, we scheduled you to go to 4:30, so Radu, it's your talk.
Yes. Would you like me to continue with this or to speak about that time?
Don't look at me. Look at your audience. I'm just a guy. I'll keep going. I mean, if people have to leave, I sent out something saying that, if you can leave, leave.
Uh,
Whatever you'd like to do, you have the floor. My next obligation is being taught by him, so I'm
going I will do only one more problem, and after that I'd like to address a topic which is extremely fun to me, the topic of average speed. And this topic was addressed by Paul Hilton, an American mathematician. He came and gave 2 speeches to Western at I don't know how long ago. This guy was, oh, okay, let me finish with. Do you see on that blue announcement, it is a problem with a boat.
The boat's not really easy to see, but it's there.
Oh. I didn't mean that is that problem with the boat that is not easily seen. I meant that it is a mathematical exercise. A boat is traveling on a river 7 hours downstream, 5 hours upstream, for a total of 76 kilometers. So 7 hours downstream, and 5 hours upstream for 76 kilometers. The speed of the boat downstream is twice as much as its speed upstream. So downstream, it travels twice as fast as upstream. What is the speed of the river? Now, here is the very important clue. Downstream is twice as fast as upstream. So therefore, in 1 hour downstream, it travels the same distance as 2 hours upstream. Is that true? Yes. So therefore, 7 hours downstream will travel as much as 14 hours upstream. So the total will be 14 hours upstream and 5 hours upstream are 19 hours upstream for 76 kilometers. So 76 divided by 19 is 4 kilometers per hour is the speed upstream. Do you see how directly we found that? And of course, 8 hours, 8 kilometers per hour downstream. Now, let me make the same picture, although not so well, like in the flyer. If the stream goes so, if we consider the speed downstream is the sum of the speed of the river plus the speed of the boat. Yes, the sum. And upstream is the difference, the speed of the boat minus the speed of the river. So we have the sum and the difference. Do you see the sum and the difference? This is the sum of the speed of the boat and the speed of the river. This is the difference of the speed of the boat and the speed of the river. We found, I gave a formula for each one of them. S plus d over 2 and s minus d over 2. This is the speed of the boat. This is the speed of the river. So 8 minus 4 over 2 is 4 over 2 is 2 kilometers per hour is the speed of the river. And 8 plus 4 is 12 over 2 is 6 kilometers per hour is the speed of the boat in still water, but this is not asked. So let me finish with a very, very, very easy and also, I don't know, problem. Let's say that Amy drove on a highway for 3 hours. At a constant speed. Yes? And after that, she lowered the speed with 10 miles per hour and drove another 2 hours. And for a total of 330 miles. The total distance. So once more, she drove first 3 hours at a steady speed. She lowered the speed 10 miles per hour, drove another 2 hours. And the total distance was 330 miles. How fast did she drive initially? And how did you get? He gave me the answer, 70. And he is right. Explain me. 70 times 3 is 200. Ha ha. No, 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 no. No, 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 no. The numbers are nice, yes, 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 because I made up as I spoke. That's why, but I could have made some. How can we solve this problem with no, once more, with no equations? Let us say that she didn't lower her speed. She drove the other 2 hours at the same speed. How far would she have driven? Because she drove 2 hours and the speed was 10 more miles per hour, she drove 20 more miles. Yes? Plus 330 is 350. 350 divided by 5, here is 70. Did I make me clear? Yes? Okay. 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 John, I don't want, if you are committed to stay at 15 more minutes, then I would speak about the average speed. If not, I will keep it for another time. What would you say? Go ahead. Okay. Let's speak a little bit about the average speed. Okay. The average speed is not like we want to think is the average of the speeds of the vehicle. If we have a vehicle which has 2 or more speeds, the average speed is not the averages of its speeds. For example, if a vehicle travels with 50 miles per hour at the beginning, 70 miles per hour after that, not only that, so 50 miles per hour and 70 miles per hour. Not only that its speed is not 60 miles per hour, but we generally cannot say what the speed of the vehicle is with only this data. We have to give also how long did it travel with this and how long did it travel with this speed. I made up an example which is completely non-reliable. So let's say we have 2 cars and they travel from here to Detroit and back in the same day. And one car made this distance in 1.4 hours. From here to, from here to Detroit. Very fast, 100 miles per hour. You will see, I have the data. And the other one, the same distance from here to Detroit, 140 miles, in 2.4 hours. This realized a speed of 100 miles per hour. This had a speed of 58.3 miles per hour. Now, in its way back, the fast car, had 2 flat tires. And instead of so fast, it needed 4.6 hours. And the other one, the same 2.4 hours. This car with 4.6 hours realized here a speed of 30.5 miles per hour. And here the same 58.3 miles per hour. Now look how interesting is extremely interesting. If we average the 2 speeds, here is 100, here is 30, 130 divided by 2 is more than 65 miles per hour. Do you see? More than 65 miles per hour. While here is the same 58.3. So, if we consider the average speed, the average of the two speeds, this seems to be faster than this. However, this is very non-true. Why? How long did it take this car to go from Grand Rapids to Detroit and back? 1.4 plus 4.6 is almost 6 hours. No, yes, it's exactly 6 hours. While for this one is less than 5 hours. So the car with a smaller time has smaller mile average speed, which is not normal. Yes? So by using the average of the two speeds is not the right way to do it. The average speed is the total distance over the total time. And if you find these two values for the two cars, here for this one is 46.6 miles per hour, while for this one is 58.3 miles per hour. And now about car race. This guy, Peter Hilton, I don't know if he is still living or not, but this guy was a very wise guy. And he was, you can ask people at Western about him and his speeches. He had at least 2 speeches at Western. And he was, why did I say was a wise guy? Because he was working in that Enigma team. Do you remember, do you know about the Enigma team, the English team who worked to break the Enigma code, the German code, and he worked with Alan Turing and all these brilliant geniuses, and they broke the Enigma code and did the work. And this guy noticed that the people who are in the car racing do the average of a car, the average speed of the car, by this procedure. Average the speeds of the cars. And basically this is not true. This is not good, as you have seen. What is the, and there is a formula for that average speed. If a distance of a lap is d, yes, let's say that a car makes 3 laps. So the total distance is 3d. Yes? The time for the first lap is t1. The time for the second lap is t2. The time for the third lap is 3t. Now, if I divide both sides by d, what I get? I get 3 over t1 over d plus t2 over d plus 3t over d, or which is the same as 3 over 1 over d over t1 plus 1 over d over t2 plus 1 over d over t3. But what is d over t1? Is the speed on the first lap. D over t2 is the speed on the second lap. And d over 3t is the speed of... So what is 3 over 1 over v1 plus 1 over v2 plus 1 over v3? Maybe you know how is this called. This is called the harmonical average of the numbers v1, v2, v3. So therefore, if you consider v1, v2, vn, the speed of a car on an n lap, then the average velocity is the same as the harmonical mean. Is n over 1 over v1 plus 1 over v2, 1 over v3, 1 over vn. Yes? Probably those guys who are in the race business didn't think that Peter know enough about car races and they didn't change. So to our day, I understood that in the car race, the speed of a car, the average speed on different laps is the average speed on the individual laps. The variation is not too large because the times are not very different. But when the times become significantly different, then there is big differences. Thank you for your patience.